to give you a very brief overview of the simulation techniques that are relevant at the nanoscale. So first thing, we have to take a look at the hierarchy of simulation methods for materials. This hierarchy means that for each characteristic size or each characteristic time, there is a typical method that covers that size or time. For example, if you want to study processes taking place up to a few nanoseconds, then you would go to first principles methods. Also, these first principles methods, they allow you to go up to a few nanometers or even 10 nanometers. If you want to go to higher, to longer times or larger sizes, then you have to go to classical molecular dynamics or Monte Carlo methods. Finally, bridging to the nanoscale, and from the limit of the nanoscale, 100 nanometers or tens of nanoseconds, to our everyday experience, then you can resort to continuum-based methods where the atomistic character of matter is not taken into account. So first, let's start with ab initio, also called first principles methods. There, the quantum character of matter is fully taken into account, and you have two large families, one with function-based, where you try to find a Slater determinant that minimizes the expectation value of the Hamiltonian, or you have density-based methods, such as density functional theory, where you try to find the charge density that minimizes the value of some energy, total energy functional. Once you have that, with these methods, you can study reactions, or you can study phase transitions, for example, the melting curve of iron, and understand why the inner core of the Earth is solid, although it is at a very high temperature. Or you can also understand other kinds of phase transitions, such as those, for example, taking place in ferroelectrics. Here you have experiment, and then you compare with ab initio simulations, first principle simulations that pose some candidates for the atomic structure, and then you compare and see if the results are compatible with the experiment or not. Then there is molecular dynamics, where what you have is you obtain the forces acting on the nuclei or the cores, and you update the positions of the nuclei by integrating the classical Newton's equation of motion, and then you start again. These forces can be obtained either from first principles or by a suitable parameterization of the interaction between the nuclei. If it's from first principles, you say that it's ab initio molecular dynamics, or if it's parameterized, then you say that it's regular molecular dynamics or molecular mechanics. With this, you can do, for example, you can study structural optimization, you can study strain release or fracture, for example, crack formation in heterojunctions or more complicated structures, or also this is typically the method of choice for the study of biological processes. Okay, so here, for example, in the study they were studying how a protein could dig holes inside the cell membranes. Finally, there are continuum-based methods which are implemented with the finite element method. Those are based typically on the continuity equation of some magnitude. This magnitude can be number of particles, can be momentum, can be mass, can be charge, okay, plus some law that relates fluxes with gradients of some generalized force. So for example, gradients of temperature that drives heat, gradients of chemical potential drives diffusion current, etc. Thanks to finite element method, we can treat very complicated domains. So here, for example, we see a heart, okay, and then with the equation of fluidics, you can study the flux inside your heart, or you can study with the equations of micromagnetics. You can design improved read or write heads. Finally, also relevant at the scale is that you can also design a new generation of equipment. For example, here a magnet, and this equipment can be used for improved studies at the nanoscale. So here, for example, later generation synchrotrons. So thank you.